So, thank you, Dave and Marios and Elaine for such exceedingly, embarrassingly kind words. And thank you all for being here. I'm really honored by the presence of so many. I'm also very happy that my family is here to share this with me. I owe so much to my parents, Robert and Joan Wellman, for love and encouragement over 55 years and counting, and for modeling life. My kids, not kids much longer, Julian and Clara, thanks for all the entertainment, and for keeping me humble, or at least trying. You are still my favorite autonomous agents. Okay. And last, but most, my wife Erica, whose love and support has meant everything. An added honor of the collegiate professorship is the opportunity to take the name of an admired individual who has served on the Michigan faculty. It is my privilege now to say a bit more to add to what Dave already said in tribute to Lynn Conway. I'm thrilled that she is here and looking forward to hear what she has to say a bit later in the program today. Lynn is all the people bulleted here and more. The list is from Lynn's website, which I would encourage all of you to visit anytime you feel the need for an inspiring story. Doing her achievements justice would take all day, so I will hit just two big points. First, the VLSI revolution of the 1980s was sparked by the Conway-Mead design principles, which Lynn developed, as Dave mentioned, as a researcher at Xerox PARC, and promulgated through special courses and design build efforts, and of course the seminal Mead-Conway textbook, whose impact really is hard to overstate. Lynn's singular vision propelled engineering practice to a degree that we should all aspire to in our own research endeavors. The story is well told in the special issue that Dave mentioned, that it was in IEEE Solid State Circuits magazine from 2012, which is also well worth your time. Second, as a pioneer in gender transition, Lynn applied her innovative spirit to her own life in a most courageous way. Since taking emeritus status, Lynn has had a second career as an advocate for transgender acceptance as well as for women in STEM fields. Lynn is a role model and indeed a hero to tens of thousands worldwide today. I am most proud to be associated with Lynn Conway through this professorship, whose name will be an enduring inspiration for me and others. Okay, now for the talk. Another perk of the professorship is that I get a captive audience for a brief time to talk about what's on my mind. Well, I'm an AI researcher, so artificial intelligence is usually on my mind. And happily for us AI researchers, it turns out that AI is on a lot of people's minds these days. As evidenced by news items we find in the major media almost every day, these snippets are just from this week. My research all these years has been about autonomous agents, decision-making machines. As I will be arguing soon, we are on the cusp of an age of ubiquitous autonomy, and so it bears asking, can we handle it? It turns out this question has also been getting a lot of attention lately in the broader context of artificial intelligence. The recent conversation, you could say, got kicked off in October 2014 when Elon Musk started saying things like this: we should be careful about AI. It's probably our biggest existential threat. Say, okay, well, he's a smart guy with a lot of insight, but just one billionaire tycoon, you know, maybe we could discount him. But then other people, like another noted smart guy, Stephen Hawking, later that year, the development of full AI could spell the end of the human race. Okay, not mincing words. Shortly after that, Bill Gates was asked in a Q&A session, well, what do you think about? Are you concerned about AI? And he said, well, why wouldn't you be? Pretty much. Now, here's another billionaire tycoon you might not know as well, Jan Tallinn, founder of Skype, who's actually studied this a bit more technically, and he's referred to that we need to really think about the superintelligence control problem, that is dealing with agents that are ultimately going to be much smarter than people. Okay, now I'm not going to be totally balanced, but not everybody is buying into this concern. Perhaps the most notable other side quote came from Andrew Ng, Stanford professor, machine learning pioneer, chief scientist of Baidu and co-founder of Coursera, who said, well, I don't really worry about evil AI for the same reason I don't worry about overpopulation on Mars. Now, I'm not suggesting he should worry about overpopulation on Mars or even that he should be working on preventing evil AI, but, and I have all the utmost respect for Andrew Ng, but I think this analogy just doesn't really make sense at all. We're going to have a lot of notice about potential population issues on Mars in all likelihood. Whereas the thing about AI is that it could come a little bit more unpredictably and suddenly. And the principle behind this is called the intelligence explosion. Some people refer to it as the singularity. That's the term that Werner Vinge, the sci-fi writer, gave to it, and what Ray Kurzweil talks about. That's a terrible term, but intelligence explosion, what is it? And this was first articulated by a hero of mine, I.J. Good, over 50 years ago. I.J. Good worked with Turing at Bletchley Park and had a very distinguished career as a visionary statistician at Virginia Tech. And he was talking about the positive feedback that would come into play once you got something that was on par of intelligence with people. Because after all, people can design machines. And if a machine can do that, then it can design itself and possibly get better. And you could potentially get a cycle of positive feedback that would lead to very rapid advances. Machines can replicate. Sometimes this is called the AI chain reaction. His conclusion, which follows very logically, is that once we build this intelligent machine, we don't have to invent anything else because it's going to be doing all the inventing. And we can close up our invention shops here at the College of Engineering at the University of Michigan. And I'm sure we'll find other constructive things to do. So again, I'm not going to go into all the arguments pro and con. It's not a done deal that this is going to happen. Will this positive feedback loop actually turn out? It's not obvious one way or the other, but it's certainly potential. It's one way that things could happen suddenly, unlike overpopulation on Mars. To give a little bit more mundane example, even short of predicting full-blown intelligence, just predicting advances in this field is quite hard. So here's a Wired article from 2014. You remember 2014, that was the good old days when people could still be computers at some strategy game. So in this article, the developer of the top computer Go program for the time acknowledged that yes, we were still only at the amateur level, but could possibly improve to beat some professional player within 10 years. Okay, well, about 1 year later, so that was Remy Coulomb, in 2015, AlphaGo from DeepMind defeated Fan Hui, a professional player, in fact, a European champion. And just a few months after that, in March of this year, AlphaGo defeated the world champion. So one point is that apparently large differences in human intelligence, say between any professional player and the best in the world, we here at elite universities like to make comparisons about relative smartness of different people. Well, maybe these seem big on our scale, but are not really big on a broader scale of possible intelligences. Maybe it's just a small change in an algorithm to span this whole differences, to span these big differences that we perceive. In retrospect, it seems understandable that we have machine superiority in Go or some game, but we have to admit it came in a very sudden and unpredicted way. Should give us some pause. So if we cannot predict milestones on narrow tasks like computer Go, one should be skeptical about predictions about superintelligence. Nevertheless, let's look at what the experts say. Vincent Muller and Nick Bostrom very recently conducted a survey of various AI experts, asking them when they thought we were likely to achieve what they called high-level machine intelligence. They defined it as the ability to do pretty much any job as well as a person. The middle curve represents the cumulative probability of the time to 50% likely high-level machine intelligence. So for example, I don't know if you could really read the graph there, about half of all experts thinks we are at least 50-50 to reach HLMI by the middle of this century. Overall, if you digest these graphs, what the collective opinion says is that somebody my age will probably not meet superintelligent AI, might, but maybe not. But my children or my students are quite likely to meet the superintelligence, and the next generation after that is very likely to encounter superintelligence. Now again, these kinds of predictions are notoriously unreliable, but it's a kind of a gauge. And just to put my cards on the table, put my little 80% confidence interval, it ranges from 2040 to the end of this century. Okay, there is, on the other hand, much less uncertainty about the emergence of narrower forms of AI, which I'm referring to as autonomous agents. Informally, an autonomous agent, AA, is a machine that is not generally intelligent, but smart enough in some restricted enough domain such that we let it make decisions without human intervention. Autonomous agents are on the verge of important presence in many significant areas, which I will talk about briefly in a moment. The claim I would like to make today is that addressing the issue of autonomy in areas such as these is not only critical in its own right, but it is probably the most constructive thing we can do now in preparation for dealing with the broader AIs of the future. Okay, so quickly through some of these in the air. The flight community is actually quite advanced in their development of autonomy. Autonomous vehicle control is often autonomous flight control is often quite feasible and established as safe in a wide variety of contexts, of aviation contexts. With the anticipated proliferation of flying drones in coming years, what is not quite worked out is traffic control. The solutions we have for human-piloted aircraft just do not scale to large numbers of heterogeneous vehicles. Fortunately, at this college, Ella Atkins and her research group in Aero are on the case. Michigan, of course, also has a huge research effort in autonomous ground vehicles. It seems that in contrast with flight, existing human driver traffic rules may work all right for driverless cars, despite the extra worries we have on the ground about obstacles, including moving ones like pedestrians, bicycles, and the like. I have no doubt that autonomous cars will eventually be much safer than human-driven vehicles, but this may take a while and will never be perfect. It remains to be seen how society will deal with robot-caused accidents. The first time that a driverless car runs over a bicycle, and this will happen. I don't know if there's any of the experts in the room, but this will happen. I expect that NHTSA or whoever is going to come in and inspect the black box. And the black box will, of course, log sensor readings and some processing, for example, tracking data. So this point cloud representation comes from some research by Ryan Eustace and his group. But we should also demand much more, such as the trace of the beliefs and the decisions of the robot driver at the time of the accident. So exactly what probability did the robot assign to that point cloud being a bicycle and being on a collision path with the vehicle? Was the decision not to swerve away justified by some other reasonable safety concern? The so-called trolley problems that have been used to study ethical reasoning in humans will, I think, turn out to be a lot more relevant for autonomous vehicles than they actually are for people. Simply because robot belief states will be more directly inspectable, I hope. It depends how we implement the robot decisions, actually. And the robots may actually get themselves in some pretty strange belief states, perhaps compared to the way people do. By the way, we also have some pretty interesting challenges in engineering these black boxes. For example, to prevent the robots from lying to us about why they acted as they did, or what they knew at the time or should have known at the time. My crypto colleagues may have something to say about this. Okay, moving to the battlefield. By autonomous weapons here, I'm referring not to the sci-fi robot apocalypse where machines take up arms against their human masters. But rather the more real concern of weapon systems that are intentionally developed by national militaries to automate their lethal decisions. The technology for autonomous weapons is actually quite near at hand. They would likely be feasible to develop if a significant effort were made within a few years, not decades, few years. Many in the AI community have become alarmed by this, as we appreciate the potential for proliferation. eventually creating a new form of WMD, weapons of mass destruction. In the wrong hands, this could, of course, be a great danger to society. There are efforts afoot to forge international agreements banning such weapons. The scientific AI community has some valuable input here, but of course these are ultimately political questions and decisions. Next, to a much less lethal, but nevertheless high stakes arena for autonomous agents, financial markets. This is the area that, as Elaine mentioned, I've been focusing much of my own research over the last few years. The financial system, as we were reminded in 2008, is crucial for the functioning of the global economy, yet quite fragile. The financial system is, after all, built out of information. And that may have something to do with its fragility. And it's also perhaps why it's one of the most highly automated sectors that we have in the economy. Autonomous agents in financial domain are already quite well established. In fact, until a few years ago, if you said the word trader, it was likely to conjure an image like this of a bunch of guys, always guys, shouting buy and sell orders to each other in a place called a pit. Well, these pits no longer exist. These guys are out on the street eating in soup kitchens. And they've been replaced by traders who live on the racks of computing clusters. And I certainly don't want to joke about displacing labor. That's actually another very serious issue about artificial intelligence. In finance, though, we're not really worried about displacing the people. We're worried about the displacement in people that can happen if the financial system collapses. Now, why would the bots do that? Well, the answer is really just that we don't know, that the fact of automation changes some things that we have little experience with and don't really understand. There are many of these, which I won't be able to go into, but the most obvious one is simply the unprecedented speed. The reason that, of course, these things are automated is that computers can react so much faster than people can to new information. And in fact, having an advantage in speed and reacting to information has kicked off a latency arms race. There are many ways that parties have found to shave off small amounts of time in their ability to react, milliseconds or even microseconds, by co-locating their servers in the data centers of the exchanges and developing new high-speed communication networks using microwave or even lasers today, by removing error checking from their software and specialized hardware, living on the edge to get that extra bit of advantage. Now, this is possibly dangerous, seemingly a large diversion of effort. These were billions of dollars that have gone into trying to get the race to get these advantages. Actually, anything that has arms race in the title, you should probably think is maybe potentially a problem. So what can we do about it? Well, it was actually what got me first started thinking seriously about financial markets when controversies arose about high-frequency trading in around 2009. The fundamental reason for the latency arms race is continuous time. In continuous time, there is no lower bound on the amount of a time difference that could matter. We could end the arms race, I proposed back in 2009, by moving to discrete time market clearing with enough granularity, say a second or a half second, such that nobody really could get too impatient, but that shaving a few microseconds would no longer convey any serious advantage. So modeling this actually is what Elaine Wah did when you heard from her earlier, when she first came here as a PhD student. What we found in our first study, which a graph is shown here, is that even beyond the waste of resources in pursuit of latency that I mentioned, the presence of latency arbitrage strategies also, in some circumstances, made markets less efficient. We've gone on to model various other scenarios trying to understand how different categories of algorithmic trading behavior affects markets and how to design markets to promote the beneficial practices and deter the harmful ones. Getting into this domain has also meant wading into the public debate. In this TechCrunch article, I argued that the latency arms race was counterproductive. After all, nothing that's very economically significant happens in most milliseconds, whereas a lot happens on our computers in every millisecond. It turns out that not all of the parties were very happy with our research findings. I am used to hearing allegations of my research falsehoods brought up mainly, but that's mainly in anonymous referee reports. So here's one that was in CNBC.com, authored by someone associated with the HFT industry. But as my wife Erica pointed out, at least he called you prominent. Okay, so I told you she was supportive. Okay. One final example of an autonomous agent ripped from the headlines, this one focusing on learning. In March of this year, as you all know, Microsoft released Tay, a chatbot designed to learn to express itself based on conversational partners. In less than 24 hours on Twitter, the internet taught Tay to be a racist, homophobe Nazi. I did not want to display the examples, but take my word for it. Tay became a very convincing bigot. So kudos to the Microsoft engineers. We know this wasn't a canned demo. Yeah, it was genuinely learning. But it's really, I think, a signal example of you put a learning agent out there and you might get surprised what happens. And this is actually an emerging research area called adversarial learning, where we have to think about what will happen. It's really getting toward the boundary of computer security and machine learning. How do you deal with the fact that some parties may be trying to teach your autonomous agents to be autonomous in different ways? Okay, so finally, let me answer the question that was posed in the title to this talk. Overall, autonomous agents promise fantastic benefits for individuals and society. I didn't emphasize these because I think they're really obvious, and that's why autonomous agents will be inevitable. There's no stopping them. With the promise, though, comes some risk, which we clearly will have to address through new methods for controlling and regulating these agents. That's technical as well as policy solutions. This will keep engineers and researchers busy with meaty technical problems for some years to come. And with what we learn from regulating these agents, we may ready ourselves for the superintelligences down the road. So just one last thing. Speaking of super intelligence, I've had the opportunity here at Michigan to work with some great minds and to contribute as best I can to training budding researchers in the way of AI. I would like to end my talk by expressing particular gratitude to the generations of graduate students who have contributed so essentially to all of the research accomplishments that I get credit for. Here are all my graduated PhDs, more or less as they look now. The SRG, Strategic Reasoning Group alumni network, stretches across the world, connecting academia and industry from big corporations to ventures, with many of these individuals active in research or otherwise using the research skills that they learned here. At least that's what they tell me. For any of you considering, in the audience may be considering a faculty career, this is the reason to do it. Not just for the PhDs, of course, but all the great students that we get to teach and learn from as they pass through this great university. So finally, today's strategic reasoning group, current graduate students and postdocs pictured here. We still have a lot of interesting research to do, and so we'll be getting back to work soon. Thank you all.
Electrode research has always been about eavesdropping on the neural activity that goes on in our brains. What we're doing is trying to develop tools to allow us to explore the brain with optics instead of just electronics. It's tektonics.